paper only came out last week before in Nature Communications Physics. Again, Louis Slocum, now a postdoc, who's taken, it's the next step to see the importance of proton tunneling. This potential is essentially, it's a curve fitted to the parameters that we get from the density functional theory calculation. So those two plots essentially give us, we have to stick walls on either side. We need to constrain the proton can't just carry on. It's held in place and in either well. So the asymmetry delta E between the bottoms of the two wells is something that's given to us from density functional theory, as is the height of the barrier. And this is looking at a single proton between G and C nucleotides. Those lines there are just the energy eigenstates in this double well potential. But you can see it's not until sort of the sixth excited state that there is any amplitude in the shallow well. So clearly, if you had an isolated quantum system and you start the proton in the ground state, it's going nowhere. It's going to stay there. It's a stationary state. You could put it in some sort of a Boltzmann distribution of many eigenstates, but even so, there'd be a tiny probability that there'll be an amplitude in the shallow well. But stick this into an open quantum system, and what you see is the environment not only causes decoherence and dissipation, but at the same time thermally activates the proton, gives it a kick. And we found that giving it a kick up to an energy level below the top of the barrier was much more likely, obviously, than getting it right above the barrier. So if it gets across to the shallow well, it's overwhelmingly more likely to have got there by tunneling through the barrier than hopping over it. In fact, this is I just pulled a few words from the abstract of our paper. So what we find is that, so the canonical form is the standard stable form where the proton's sitting in the deep well. The tautomeric is the unstable shallow side. The canonical and tautomeric forms of GC interconvert over timescales far shorter than biological ones. That quantum tunneling happens over femtoseconds. And as far as biology is concerned, that's too quick. But that doesn't matter. What it means is at any given moment, as far as the biological system is concerned, the state of this proton is in thermal equilibrium. There'll be a certain fixed probability that you could, at any one moment, if you take a snapshot, that there'd be a fixed probability that you'd find it in the deep well or the shallow well. So it reaches thermal equilibrium rapidly, and we calculate that the occupation probability in the shallow well is 1 in 10,000, which is huge. Previous estimates were like 1 in a billion. There's a 1 in a billion chance that that proton will be sitting on the wrong on the wrong site when the strands separate, or at any given time. But we find it's much higher than that. This is the first time anyone's done an open quantum system calculation. People have used density functional theory and used various approximate chemical, chemistry techniques, or they've used WKB approximations or whatever, and they get very small probabilities. Even though we're using a Caldera-Leggett model, which is, comes with various assumptions and simplifications, like the fact that it's Markovian, the environment is ohmic, it's a high temperature approximation, which actually is fine for biology. Nevertheless, it suggests that the tunneling probability is much higher than people had thought before. The next step, something else that we're doing, a paper that, again, there was also published this year by two of our other students, Sapphire Lally and Nick Wareham, looks at going beyond the Caldera-Leggett model, looking at non-Markovian corrections. And again, there are many people working on non-Markovian corrections, and there's a whole industry here. The technique that in particular Nick Wareham developed was to say, what if the environment, so if the spectral density is just proportional to the frequency of the oscillators in the bath, what if you put up a high frequency cutoff? So you're saying, the bath oscillators don't go all the way up to infinity. There's a maximum frequency that beyond which there aren't any oscillators in the bath. Already you've gone beyond what is a Markov approximation there. And then Nick developed a technique for developing some expansion, a series expansion in powers of 1 over this maximum frequency. So this cutoff frequency is some large number. So 1 over the frequency in a power series expansion. Looking at the leading order correction, that will be the leading order non-Markovian term on top of the Markovian approximation of caldera-Legge. So we're putting in non-Markovian corrections. And what we see, so what you're looking at here is, if people are familiar with the famous, there's a Physics Today article by Zurich on open quantum systems, where you start off with something in a superposition of 2 Gaussian peaks. This is a plot of the spectral of the density matrix. So the line across horizontally, those 2 peaks are sitting on the diagonal of the density matrix. The 2 lines the 2 bumps vertically, those are the off diagonal elements that describe quantum coherence. The left column here, what I've called R equals 0, that's the standard caldera-Legge Markovian version. On the right-hand side is adding in this non-Markovian correction. And we're dropping down in time sequences. So you can see very quickly the off-diagonal elements disappear in both cases. But what we see is some weird resurgence of off-diagonal rippling effect on either side of those peaks on the diagonal, which we've called lateral coherence. There are various ways of measuring quantum coherence. We've used a quantity called the L1 norm. So it's basically a measure of just to what extent this thing has decohered and it's gone from a pure state to a mixed state. The action of the environment. You can see that the line that's at the very close to t equals 0, that's the initial rapid decoherence that we see from the first figure down to the next one. The different curves here are different amounts of non-Markovianity in our model. And what you can see is there's this resurgence. And so this is the early stages. We want to understand how important is it that our environment, we have to treat it more carefully than the caldera-Legge, the Markovian ohmic environment. The reason why that's important is because if in living systems, quantum coherence can be maintained for timescales that can play a role in biology, then there must be something clever going on. The environment can't simply be white noise. It can't simply be an infinite heat bath that's just sucking away coherence, like putting a hot cup in the freezer. The environment, as described by its spectral density, may have structure. There may be certain frequencies in those the bath of oscillators that are more important than others. So imagine sort of spikes on top of the spectral density. And it could be that life has had plenty of time to evolve trickery, to tweak the nature of the what to do with the vibrational frequencies of these molecules that act not to cause decoherence, but to somehow resonate with the quantum system itself, in this case the proton, and maintain coherence for longer, for long enough to play a role in biology. That's still an open question. At the moment, in fact, this paper, for example, the word biology doesn't appear in it. Okay, this is just purely a theoretical physics paper. But we can, the motivation for doing it is that maybe there's something happening in biological systems that Erwin Schrödinger would have been very pleased to hear about, that maybe we have to look more carefully for. I want to end just by saying that I set up a virtual quantum foundation center, to bring together various people who are interested in some of these ideas. And also because, as a nuclear physicist and in the tradition of my PhD supervisors, I sort of was discouraged. I was talking with Simon about this earlier, discouraged from talking about foundational issues in quantum mechanics. You know, if you weren't a Copenhagenist when, you know, I was a student in the 80s, it's sort of, you had to keep your head down, right? You whisper, if you know, I quite like Bohmian mechanics, you know, and even weirder if you're a many worlds advocate. And so I've sort of reached that stage in my career where I'm quite happy to sort of explore some of these. And also, I think we're getting to that point where a lot of physicists feel we have more freedom, to be more open about some of these foundational issues. So I'm sort of linking that in with some of these ideas in quantum biology. Recently, we received a large grant from John Templeton Foundation called Life on the Edge, Quantum Thermodynamics, Quantum Biology, and Arrow of Time. It's basically a collaboration of 6 universities led by Surrey, including Oxford. So at Oxford, of course, Simon is one of 3 philosophers of physics who are named on the grant that we're working with. We also have Vladko Vedral and Chiara Marletto here at Oxford, who are part of the team. Then we have other philosophers, Karim Thibault at Bristol, Eddie Chen at San Diego. We have Paul Davis at Arizona, and we have a group of experimental quantum biologists at UCLA who are carrying out some experiments. There are lots of different strands to the work. So we're looking at open quantum systems and biology. The big motivation for this project is really on issues on the arrow of time. And, you know, while listen to someone like, you know, Sean Carroll will tell you that everything in the universe is time reversal invariant plus the past hypothesis. So, you know, so the arrow of time is only about increasing entropy. You don't need to worry anywhere else. I'd like to see if I can understand more about the irreversibility of the arrow of time down at a quantum scale when we go from an isolated to an open system, linking with things like the measurement problem. And that's where it links in with foundational questions in quantum mechanics. And so this is a really exciting group. We have 16 people named in the grant, 3 philosophers, half a dozen physicists. We've got a couple of computational chemists. We've got 2 applied mathematicians and 2 molecular biologists. And we'll see where it goes. I just wanted to then end by acknowledging both Leverhulme Trust, of course, for our Doctor Training Center and the John Templeton Foundation for funding this new project. I've mostly worked with John Joe McFadden, molecular biologist. Andrea Rocco is a fellow theoretical physicist. He comes from statistical mechanics. Marco Sacchi is a computational chemist. Then we have our PhD students. And I want to leave you with perfect timing. It's very good, isn't it? I want to leave you with an announcement of a forthcoming meeting. Part of our John Templeton Foundation project is quite a large activity in outreach and doing lots of different other fun things. Somewhere between our head down work and sort of sticking our head over the parapet are what we're calling a series of blue sky thinking workshops. So they're very similar, if you're familiar with the FQXI series of meetings, where people are deliberately provocative and speculative. And so we have the first one happening this July. It's entirely online. Next year, we're hoping it'll be face-to-face at UCLA. And then the following year, we'll be back in the UK, somewhere in London. We already have a program. This is going to be announced. So in fact, I'll be very happy if you have a mailing list that we can send this announcement round. So we have our speakers already. So it's a mixture of physicists and philosophers. The idea is that these talks, that people are free to say what they want to talk about, and as long as it's loosely connected with some issues to do with the arrow of time and irreversibility. And so we hope as many people as possible can join us online. But otherwise, thank you all very much for your attention.